Hello again, and we're back talking a little more about board plots, specifically looking at some problems to help us understand the concepts that we covered in the last lecture. So here I am looking at slide 33. I think this is 33. Sometimes these slide numbers 32, yeah. So 32, I showed you this slide in the last recording, and it's a summary of the magnitude plots and the phase plots for different terms in the transfer function. So for the constant term, for a zero at the origin or a pole at the origin, for a simple zero such as 1 plus j omega by z1, or a simple pole. This is what it looks like at the bottom of the screen. So we've seen these shapes, and then I also talked briefly about complex conjugate poles, which tend to be always slightly more complicated. But we covered all this, and so I come to slide 36 so that we can begin the fresh material and actually solve some problems with some real values for circuit values such as uh, factors like s plus 1, s plus 10, etc. in the transfer function. Okay, so this slide I just wanted to point out that obviously we are going to, the whole world of engineering relies on computer software to do this kind of work, no doubt. So in fact in lab 4 you will have an opportunity to do board plots using, I think, MATLAB and multisim, or one or the other or both. But obviously for complex circuits we will rely on computers and computer software to help us draw these plots. Nevertheless, I think it's important for all of us to understand how exactly the computer proceeds. What algorithms, what rules does the computer program use to be able to do the job quickly and faster and probably more accurately also. So I just wanted to show you a sample of a computer generated plot, and then we will actually get into some real problems. So on the top left is a circuit. It actually is a what is called a pi filter, and that filter circuit has been plotted, or its frequency response, both magnitude in decibels on the top and phase on the bottom, they've both been plotted, and you can see what it looks like for a complex circuit. We will certainly not try to do anything this complex manually, right? In the old days, I think maybe 30 years ago, a lot of us had to do these things manually for complex circuits, but these days you're just going to use multisim to do it. Okay, so anyway, looking at the two plots, you might find something meaningful here. So for example, it has a nice looking at the magnitude plot, and this is a interesting situation because the frequency range that they're interested in is 0 to 1 hertz. So they've actually expanded the scale for 0 to 1 to see all of the little details within that 0 to 1 span. So until it's 200 millihertz, the magnitude is just a 0 dB, but then it drops to minus 50, and I think it stays at minus 50 for a long time. Similarly, if you look at the phase angle on the bottom, it starts at 0, falls to around minus 150 or so, and then ends up being minus 90 roughly after 360 millihertz and all the way. So interesting circuit. Let's not worry too much about it, but I just wanted you to appreciate that this is how real plots are going to look like. Okay, so I moved to slide 37, and we have some things that we can learn from here. Actually, let me also expand this. Yeah, okay. So, in a general case of still a somewhat simple transfer function, as you can see, there is a constant term a, and then there's a 0 on the top, s plus z, which is a 0 is at s equals minus z, and there's a pole on the denominator, s equals minus p. So that's how the S domain transfer function would look like. And then when you're given something like this and you have to solve, one of the first things we do is to take the logs, because once you take the logs, you're able to actually look at the individual magnitudes and the individual angles of each of those factors, each zero, each pole, the constant factor, and separate them out. So you can see how the formula works, and that is thanks to the fact that logs have that property. Multiplication becomes addition when you take the log, and so on. So the first step is always to start taking the log. And anyway, we define a lot of these magnitude plots, etc., or board magnitudes in terms of logs. Anyway, logarithms, right? So the first step is to take those logs, and I wanted to show you that this is the way you open up the formula, the transfer function, if you're given a transfer function like is shown on the top here. One other thing I wanted to point out, just so you have this in the back of your mind, we have look at the three items split individually. So the first item is for just the value a, the constant a, so that becomes 20 log a. The next one is 20 log s plus z for the 0, and the denominator, you can do it one of two ways. You can either say plus 20 log 1 by magnitude of s plus p, or you can put a minus and just bring the s plus p to the numerator. Either of these works, and again this is a property of the logarithmic property also. So either of these will work. So I just wanted to show you that in case you ran into this and you were a little unsure about how all this happens. Then at the bottom we have how do you calculate the net phase angle, right? You can calculate the individual phase angles, and those are shown as psi 1 minus beta 1 minus beta 2, and then phi, the total phase angle, is the sum or difference of each of those. Okay, so actually I'm sorry, this should be a plus. I'll fix that. Oops. Okay, I think that should be a plus, and now we are good. Okay. So that's the formula for the phase angle, and each of the individual angles are tan inverse of something. And of course, for a constant, there is no phase angle, so that's a 0. Okay. So that was a general form, and now, as promised, I have some real good-looking transfer functions. So here is one method from one textbook. Now, different textbooks have different approaches. I don't want to confuse you. I try to pick one that is, what we have in our textbook, our Nielsen textbook. But even there, I feel that the material isn't covered, very well, not perfectly. So I brought in some extra material from here and there. So hopefully with all this, you get a clearer picture, and that's my goal. Okay. So anyway, how is this problem being solved? So we have one 0 on the top, a constant term, and a pole, right? So what are the steps to start solving this problem and getting these nice plots? So what do we need to do here? We need to find a straight line approximation of the board magnitude plot, and next step, next slide, we will find a straight line approximation of the board phase plot, phase angle plot. Okay, so how to proceed? Okay, so first you open up the transfer function and try to bring it to the standard form on the top right, right? So the standard form is in omega, it's in the frequency domain. So first of all, we try to substitute j omega for all of the s's. So the s goes away, j omega comes in. Also, we have to calculate this constant in the standard form 1000, right? Here it came out to be 1000. How do you do that? You take the original constant, then you look for any other factors such as this 100 and bring that out, and then that becomes 10 into 100 into s plus this should be s into 1. Sorry, I should fix all this before I start my lecture. I know. Okay, so s in plus 1 by 100, and so that's how the and here there is nothing, it's only a 1, so 1 comes out. So this constant in the standard form becomes 1000, and then you put the j omegas in place of the s's, right? Okay, so I hope that's right. But anyway, this is the standard form on the right. So finding the Bode magnitude plot, straight line approximation. So we have this standard form, so we're going to take the logs on both sides, and so this h of s in decibels becomes 20 log 1000 minus 20 log the factor that's in the denominator, which is the pole, and then you add the 20 log of the numerator again, the 1 plus j omega by 100, right? So if you factor out some of these immediately, or if you calculate this 20 log 1000 is 3, so you get a 60 decibel answer there. These two, they are still going to remain in omega form, and so we have to start plotting them. But we can write the fact that this has a breakpoint at omega equals 1, that's this 1 on the denominator, and this has a breakpoint at omega equals 100, which is the 100 in the denominator. By the way, I'm on slide 38 in case I didn't mention that before. So what I've done here is, actually I borrowed this from another paper. So what that author of that paper has done is to put individual graphs for each of these three factors, right? And then he adds those together to come up with the final. So there's two ways to do this: individual, add it, and final. One, you can draw the way it is shown. Another approach is to just create one big semi-log graph paper and plot all three on the same, and then it makes it easier to add, okay? And we look at both methods because that's the second method is what has been followed in our textbook also. But I feel knowing that there are these two approaches available will help you understand how the final result comes together, okay? So let's look at each of these three here. So we have the 60 decibel and it's a constant, so there is just a constant line, right, at 60 decibel and nothing more to talk about. The next factor is the pole, right, which is originally it was hs equals 1 by s plus 1 as given in the original transfer function. So how does that plot? Now if you remember in our summary sheets in a few slides ago, I said when there is a pole, it has two pieces. First piece is 0 decibel and the second piece is a minus 20 decibel slope pointing downwards if it's a pole, and the break frequency or the break point, the corner frequency, is whatever is in the denominator. So in this case the corner frequency is 1. So at 1 you have the break point, and up to the break point from 0, and this is, remember, this is in radians. The x-axis is in radians in case you didn't spot it, and the y-axis is decibels as shown here. So up until 1 radian the response, the magnitude is 0, and then it begins to drop at the rate of minus 20 decibels per decade. And you know what a decade is? It's a 10 times multiplier. So if you look at any 2 points on the x-axis, correspondingly there should be a drop of 20 dB. So if this is 10 minus 20, this is minus 30, this is minus 40. So from minus 20 to minus 40 is the drop when you go from this is 100 to 1000 on the scale. Okay, so that's how you account for the pole. Now let's look at the 0, right? The 0 is s plus 100, which means its break frequency is 100. It follows the same rules. It's 0 until it hits that break frequency, and then it starts to rise at the opposite rate, which is plus 20 decibels per decade, right? So I hope you see how these three factors have been plotted. Now you add these together, and obviously you have to be careful how you add it, but the starting point is always this, whatever the constant begins at, so that's 60, because this is going to be 0 and this is 0. So until you reach this point 1 or radian 1, which is here in the output or the sum, it's just 60. From there on, at least for one more decade, that is from 1 to 10, there is just this drop, right? This guy is still sleeping at 0 at that point, right? So from 1 to 10, it stopped. The drop is at least up to 10. This is, it's the same. We need to only worry about how this is changing after 1, right? And so after 1 until 100, it's only the effect of this pole and whatever is the 60 decibel, right? So the 60 decibel minus whatever the values are here, this is minus 10, minus 20, minus 30, is what is going to be shown until 100, right, which is 10 square. Then at 100, all three now have a role to play, right? So at 100, you have this 60, and then this guy, if this is 1, this is 10, this is 100, he has already dropped to minus 40, and this guy is at still at 0, right? At 100, he's still at 0. So we have 60 minus 40, which is minus 20 at this point. And from then on, it stays flat again, because every increasing point after 100 has a counter decreasing point because of the pole. So they balance out each other, and since we began this balancing act at 40, so actually somewhere here at 40, minus 40, so the 60 minus 40, which is 20, is all that remains to infinity. Okay? So I hope you are able to take the individual components and sum them up to come up with this form. Okay? So that is what I wanted you to take away from slide 38 and the way this example has been done. Now there is a part B to this same example, and let's look at that. This is to find the phase plot, right? So far what we have done is the magnitude plot, and now what we are going to look at is the phase plot. So the phase plot again has three components, right? The constant term, the first term because of the pole, which has a minus factor, and then we have this which because of the 0, and that comes with a plus factor. Okay, so So look at how the pole is being handled first. Okay, if you go look at the summaries and what we have done already previously, the rule for plotting the phase angle plot for a pole is the following. Again, pick the corner frequency, right? In this case, that's 1. So at 1, you will have a minus 45 degrees. Same thing here for the 0. At the corner frequency, you will have the graph, the plot, stopping at 45 but with a plus sign, because this is a pole, the phase angle goes in the upward direction. Here the phase angle drops from 0 to minus 90. Here it goes from 0 to plus 90. Okay. So first of all, find the 45 and minus 45 point. Then 1 decade on each side, on the left side and the right side. Find the neighboring frequency 1 decade less, and at that point you can stop the straight line plot from 0. So from 0 to, in this case, 1 by 10, the straight line plot runs 0 to 10, 0 to 1 by 10, and then stops. Similarly, on the right side, after 1 decade, right? So we are at 1 here. So after 10, again, it will resume to be straight line, but now it will have dropped to minus 90. So this is a 45 degrees per decade drop, right? 0 to 45 and then 45 to 90 in 2 decades. And so you join that by a straight line. Similarly, here you join from the 10 to the 100, going through 45 at the corner frequency. In this case, it's 100. Draw another straight line. So 3 straight lines, 1, 2, 3. Similarly, here 1, 2, 3. Okay. So I hope this was clear. Now in this graph, the actual and the correction, etc., is all shown. For the moment, let's not worry about it, but just look at what I call the straight line approximation and see if you can understand how exactly that came about. Okay. Now, when you add these two, it takes this form. Okay. If you look at the straight lines, they form a V in the middle, and then this is what it looks like. Forget about this dotted blue. The reason it's there is because in this textbook, the author wants to ask us to consider this straight line as the asymptote, as the straight line approximation. But that is unusual. It's not too common. Some authors take that position, but it's not too common. So ignore entirely this blue line. Go with what I call the straight line approximation I show you here, which is that angled line, angled at 45 degrees per decade, because that is in our textbook and a couple other textbooks also. So I'm more comfortable just showing you, to stick to this straight line approximation, the solid blue line. Okay. Now you can do a little bit of math to understand how this V shape comes about, but all you have to do is to look exactly at this 10. See, the two 10s are lined up in this case. So if you think this drops to 0 to 90 and this picks up from 0 to 90. Okay, so the way to think about this, the joining the two, obviously, is the fact that for the pole, we started tracing, even if you follow only the straight line, and we are at minus 90, right? So we dropped minus 90. Now, once you hit a pole, once you hit a 0 at that point, then you start following this pattern, these rules, right? But you don't obviously, you're not starting at 0. This is the case if there was only one 0. Obviously, because the two are together, you have to think of them one after the other. The effect is one after the other. So the pole leaves us here at minus 90, and from here we start climbing back up. First we climb up to 45, which happens when the frequency is 100, which is the break frequency for the 0. And so you climb up to that 45, and then in another decade you hit the 0 point again, right? Meaning you hit the highest point, which would have been another 45 degrees from here. So 45 to 45, but that just brings us back to the 0 point again, the 0 phase angle again. So after all is said and done, because of the effect of these two, a pole and a 0, if you look at very high frequencies, well beyond what you see here, then what we are saying is the net phase angle is likely to be 0 degrees again. Okay, so that's how you put these two together when you have a problem with a set of poles and zeros. I also wanted to quickly introduce the idea of the corrections. Actually, let's see, what do I have on the next slide? Yeah, I have some more material on the correction from our textbook. So maybe we'll read this, whatever the textbook is saying, and then come back maybe and look at that correction one more time. Okay, so we talked about the fact that the straight line approximations, or asymptotes as they are called, they're easy and quick to draw. You don't need, there's a straight lines, right? So you can, anytime you have a problem, take a semi-log paper and just draw some straight lines with your pencil and ruler, and you have a good idea. But there are some rules that tell you exactly what corrections you need to make to the straight lines so that the actual curves of the magnitude and the phase angle also can be shown. These are not very difficult if you have the extra time and you're looking for a very high degree of accuracy, particularly around the corner frequencies or the break point. Then you follow these rules. Okay, so what are these rules? I've copied most of this from the textbook, so you can see this. It's in section E.3 of the chapter. For the magnitude response, again for first order poles and zeros, number one rule, at the corner frequency, the actual value in dB is plus or minus 3 dB. Okay, so while we say it stays at 0, that's the straight line approximation, or the green line here in my previous example. If you assume that straight line, that's a straight line, what this rule is telling us is, if it's a pole, then the actual value, which is the shaded blue colored value, the actual curve is shifted minus 3 dB below the 0 point, if this is a pole. Similarly, for a 0, which is here, the 3 dB, it's a plus 3 dB correction. So you actually, most textbooks just leave you at the 3 dB and say, okay, make a correction at the 3 dB and then sketch the rest with a pencil and you'll be okay. But here in our textbook, he gives us a couple more points. He says at half the corner frequency, so if the corner frequency is omega c, then omega c by 2, you get the actual correction as plus or minus 1 dB decibel. Similarly, at twice the corner frequency, that is, if this is omega c, then twice of omega c, is a plus or minus 7 dB correction. So somewhere here, it's actually not so much a correction, but it goes to an absolute value of plus or minus 7 dB. Okay, so look at this point, right? At 2 omega c, he's showing us an actual value of plus 7 for the 0 line, right? So from 0 to the actual blue shaded line, the gap is plus 7 dB, and the correction he shows you is just 1 dB. Okay, while here the actual line is 3 dB, because we are starting at 0, you can say the correction is also 3 dB. So anyway, this is the logic behind the correction business, and so here I show you the same result I showed you previously for this problem, and I show you not only the straight line approximation but also the actual value. Okay, so this is the correction you apply from your straight line approximation. Let's also look at the correction for the phase domain, phase angle plot. Okay, so the phase angle plot, as we know, is like this, right? By now I hope you have gotten used to it. The green here is the phase angle, and I'm on slide 41, by the way. So if this is the break frequency, 1 decade before the break frequency and 1 decade after the break frequency, you get to the flat portion, right? So there's flat, then there is a straight line, a slope straight line, and then there's a flat. And this has that 45 dB per decade slope, and it has a midpoint of 45 degrees or minus 45. In this case, this is a 0, so it's pointing upward. If it was a pole, it would point downwards. But here, the midpoint is plus 45, and the angle line, the slope line, goes from 10 to 100 or to 1000, right? Going through 100. So that's the green. Now we draw the actual shape of the curve, okay? And you can see that the actual shape is twisted. It's like a sine wave around this particular 0 point, right? So that's the actual shape. And here on the right side, the author, the textbook, gives us some more rules about how to apply corrections, okay? He doesn't say too much except to make the following point. The maximum deviation between the straight line approximation and the actual phase angle plot. So this is the straight line, the solid line, and the dashed line is the angle plot. The phase angle correction is plus or minus 6 degrees maximum. That's the maximum. So there can be lesser values, then the correction can be less than plus or minus, but the maximum happens at the deviation, right? This is the maximum deviation, and so that is the correction. So how do you apply a plus or minus? In this case, I think somewhere here at 10 times x, right? So if this is let's say P1, let's pick the pole, which is this portion. If P1 is here, this point, then the maximum happens at 10 times that PVN, which is somewhere here, and here the deviation is supposed to be 6 plus or minus plus 6 degrees. Okay, so pay some attention, see if you understand this logic, and in fact I show the correction here also, and I think this may be a little bit clearer. Here there is a 6 degree correction, and I think this is probably not quite right, so hold on, let me fix. Yeah, let me verify where exactly that happens. But for now, let's just say that the correct? The maximum is plus or minus 6 degrees. There's a minus 6 here and there's a plus 6 here. Yeah. So I'll figure out what exactly the value is at what frequency that occurs. But nevertheless, the magnitude is correct, and that's plus or minus 6 degrees. So hopefully you understood this issue related to how you correct for both the magnitude value, where it's a plus or minus 3 decibel normally, and here it's plus or minus 6 degrees. Okay, all right. So that was slide 41. Let's move to slide 42. There are 3 or 4 examples in the textbook, so I picked one. There's actually no problems in the back, so we only have to worry about examples. One other thing I wanted to also say from a test quiz point of view, I'm not ever going to ask you to actually draw a full board plot for a transfer function. It's not really necessary anymore to have that detailed knowledge, because like I said, you're going to anyway use a multisim or MATLAB to do these. But on the other hand, I may ask you a simple rule, such as if it's a pole, let's say 1 by s plus 20, then what is the break frequency? And then what happens at the break frequency. So if you know some general rules, that should be enough for a test or a quiz perspective. You don't really need to solve a full problem, although I think I'll give you at least one homework problem so you guys can try and sketch this roughly on your own. But this is not going to really appear in a quiz or an exam. Okay. On the other hand, do make the effort. I know we have a lab also where you'll have the chance to exercise using multisim. There you should become more proficient or experienced with this. Okay. So having said that, I want to do 2 more problems. Actually, they are both about the same circuit, RLC series circuit, same transfer function. Example E1, he asks us to plot the magnitude plot, and E2 plot the phase plot, okay, phase angle plot. So they are just the same problem, but it's in 2 pieces. And then there's a few extra things that he's asked us, and we'll go through all of this. Now, all this has been solved quite well in the textbook. Please follow along in the textbook, pay some attention to the textbook. If you have time, please read it. It'll be beneficial. I'll try to walk you through, I think, a little extra clarification on some of the ideas in the textbook will also be beneficial. So let's take another 10-15 minutes and do these 2 examples, E1 and E2, from the textbook. Okay. So we see an RLC circuit and a series circuit, and he wants us to find the transfer function as the Vout output, which is, remember, the output voltage across the resistor, not the capacitor. It's kind of slightly modified, but anyway, output by input. Then B, construct a straight line approximation of the board amplitude plot. Okay. 3, he says, using what we found as the transfer function and its magnitude as 20 log something in decibels, find the actual magnitude at omega equals 50 and omega equals 1000. And then obviously you're supposed to check with the plot to see if your values are correct. And then last point here, D, is if you're given a certain input, which is as a cos function, as a cos excitation, then what does your board plot tell you about the output, right? So you should be able to say from your board plot, okay, the magnitude is so and so, the phase angle is so and so for the output at various frequencies. So given that my frequency omega is 500 in this case, and the phase angle, initial phase angle is 15, what will be the output? Okay, So that is something that you're supposed to do. Similarly, there are some requirements for E2 and we'll come to that in a bit. Okay, so I'm going to skip to slide 43 where we start to solve the problem. So first of all, we need to find the transfer function, right? And I'm sure you know how to write the transfer function. First you convert to the S domain and I show you the SL and 1 by SC values. Write a transfer function in S and then also factor. Luckily in this case it's just real roots, so this is how it comes out to be. Okay. Now I'm going to skip to slide 44, the next slide. Continuing, so we have this nice transfer function in S. Now we have to find the transfer function in the frequency domain. So substitute j omega and you get that. Now you also need to convert it into standard form, and I show you the math here on how to convert to the standard form. In the standard form we have one 0 at the origin. That's what the j omega on the top stands for. 0 at the origin. And we have two poles, two real poles. One of them is at omega of 10 and another one is at omega of 100. Okay? And then this 0.11 you see, and how it's converted to dB, I'm already telling you that that is the starting point of the board magnitude plot, which I think you saw that earlier also. Okay? Alright. So moving on to slide 45. Now I'm going to use the same method I showed you previously, where I do each of these separately so you can see clearly. Then I also show you, I think a bit later, I just copied on slide 48, I copied the graphic, the image from our textbook, from the solution in the textbook. So depending on which one you like, you can use either method, right? In the textbook solution, as you can see, I'm on slide 48, I apologize for skipping ahead, but I thought I want to make the distinction. The blue shaded line is the final answer, right? And that final answer is the sum of three individual plots. There is this plot, there is this plot. So this plot is for, actually there should be a total of 4 plots. Yeah, there's actually a total of 4, okay? Because there's also the constant term, right? The 0.11. So there is a straight line for the 0.11. There is an angled straight line for the 0 at the origin. Then there is a downward sloping pole at omega equals 10, and then there is a downward sloping pole at omega equals 100, right? That's the other one. Where is that shown? Yeah, so you can see this line and this line. So there's a total of 4, and then point by point you can add these and come up with the blue colored result. It would help if we didn't have these horizontal semi-log scale lines, but with all these lines this can be a little bit confusing, but nevertheless this is also what is commonly used in a lot of textbooks. Okay, so this method is good. I will go back to the other method I showed you where we are plotting individually. Okay, so how do I do this? Again, I take the transfer function, the original transfer function. Obviously this has to be in the frequency domain. So in the frequency domain, the standard form of the transfer function is what we have here, and I identify the corner frequencies on the top right. Now we take this and do the log on both sides so that we can expand the terms and do the addition and subtraction. The division and multiplication convert into addition and subtraction. So on the left side we just log the whole thing and say that's going to be the answer in decibels, and on the right side we have these 4 factors, right? So the two of these factors I put into one graph, and the other two, the two other poles, I've taken them out into two separate graphs. So for this, you can see on the leftmost side, the first factor, the constant 0.11, right? The 0.11 just leads to a flat line at minus 19.17, because minus 19.17 is a decibel equivalent of 0.11. So that is one line. I think you understand that. The next is 20 log j omega, which means at omega equals 1, if you substitute omega equals 1 in this and you take the absolute value, you will get a starting point at 0, because log of 1 is 0. So you start at 0, and then it has a natural slope of 20 dB per decade, right? Same thing as these other slopes, but you can check in 1 decade. So going from 1 to 10 or from 10 to 20, if you plot, it goes up exactly 20. So it goes from 20 to 40 when you go from 10 to 100. Okay, so that is this line. Now we come to the other two factors, which are both poles. One of them is at a frequency of 10, another one is at a frequency of 100. So by now I hope you know how to draw the two portions and make them meet at the corner frequency. So once you've got this together, you can create the total, the resulting output, which I show in green. Okay, so at the starting point, for example, you have a 0 and then you have a minus 20, right? And these are still 0. So 0 and minus 20 gives you the starting point of minus 20. Then pick a couple points so that you can add the these values individually. So for example, at 100, right? At 100, what is the story? So at 100, this is still that slight value of minus 19, right? Right there. At 100, this is already hit 40, right? At 100, this has hit, if this is 0, this is minus 20, right? Okay. And at 100, this is still 0. So if you add all of these, this 40 minus 20, which is minus 20, no, plus 40 minus 20 is about 20, plus 20. Plus 20 minus this 19, minus 19.17 gives you like 0.8 or something, right? And so that small value 0.8 is what you see from here to here. Okay, and then it starts to fall off. Okay, so I hope this is helpful in visualizing how you can take these individual plots and come up with the total plot. If you prefer, when you have to do a real problem, you can do the other method. Again, I'm going to slide 48. Try to find some paper that doesn't have these solid lines, but it only has lines at 1, 10, 100, 1000 and so on, because these solid straight lines, they do more harm than good. I think they give a very busy picture and it can be confusing. So if you can find good plotting software or plotting paper, then you can just plot each of these directly, and then it makes it easier to just pick any point, look at each one of the values and the total value. Then so for example, you can look directly here, this point at 100, which we just did, right? This point at 100 is the sum of this 40, this minus 20, or minus 19, right? That line here, and then the other line is at minus 20. So there are two different points here, but they're slightly separated, okay? And then this one, of course, is still stuck at 0. This last line, which is related to the pole with a break frequency of 100, that is still stuck at 0. So that is not contributing anything. But the other three, you add them together, you come up with that slightly positive value right there, okay? So that's how you can do the math, okay? Boy, we're already at the time. So give me 5 minutes and I'll wrap this up. Okay, so we did this. We have a couple more things to do, like I said. So part C, he says, at two different frequencies, omega is 50 and omega is 1000, find the absolute value, right? And so we calculate, and then we can check to see if these values, at least approximately, are accurate on the actual plot that we just created. And I can tell you that this is absolutely accurate, but here we are calling this minus, it's calculated as minus 0.311, but our plot shows it slightly positive. Now remember, these are straight line approximations, right? They're not actual graphs. So the actual graphs can be slight decades or slight dBs up and down, particularly near the corner frequencies. Okay, so remember that, but otherwise they should be roughly matching each other. Okay, then he says predict what happens if you have an input of a certain magnitude and phase. So find the amplitude. He finds the amplitude one way. We look at the amplitude in the plot, and we can find that they are similar to each other. Okay. So that is shown how to do it in the textbook, so please go ahead and do it. The last part here that I want to quickly finish is how to do the phase angles again, because we have to construct the phase angle plot also, right? So here we have these three factors and they are related through this formula. So the three individual is the method I've shown you before. You can draw these straight line approximations going through the 45 degrees in each case, one at 10 radians and one at 100 radians, right? This 45, and then you add the three together, I get the shape. He has done the same thing using this mixed approach, or use one sheet of paper to plot all three and then add them. So either method you use, you're going to end up with the same value, but I hope both methods together give you a good sense of how to go about calculating. So these other items are solved in the book, so please pay some attention and go through them. He again wants us to calculate the phase angle or the net phase angle at different omegas and then show them on the plot and see if they match. Okay, and then also find the V0t for a different VIT using the board plot, and you can see how that has been calculated. Okay, the very last step, I'm not going to spend too much time, I apologize, but we also are supposed to have done a problem or two on complex poles and zeros. These are harder. I think you know the logic by now. We have talked about complex poles. You now have these new factors, omega n, zeta, and they all contribute to making the shapes look like this. But I don't think we really need to solve a complex pole zero problem. We are in the age of computer software. We let the computers do it, but do take some time to understand that the methodology, that this is the approach you should use if you run into a situation with complex poles and zeros, at least to understand what the computer is doing. So different damping functions lead to different shapes, and different corrections also for the straight line approximations when you have complex poles or zeros in the transfer function. Okay, so that brings us to the end of this entire chapter on frequency response. It's a big complicated subject, but I hope some of the basic stuff you're able to understand. We will continue looking at frequency response in our next week also, next week's material on filters. Okay, all right, thank you.